Hello, Honors Chemistry, and welcome to the second part. I think there's just going to be two. We'll see. The second part of the Chapter 12 review. So first we talked about types of IMFs, relative strengths of IMFs, right? And other things to consider as we rank them, okay? Or apply them to real molecules. All right, so then we have our properties that we talked about in this chapter, right? For liquid properties, what did we talk about? Right, we talked about viscosity, which is what? Right, resistance to flow. So high viscosity means high resistance to flow. So we think of things like honey and syrup, right? We also talked about, right, surface tension. And what is surface tension? Right, surface tension is the tendency to minimize the surface area exposed to the air. Yes, minimizing the surface area exposed to the air, right? Which is why, for example, if we think about water droplets, right, that's always the go-to thing, right? Water forms neat droplets, spherical droplets, right, to minimize, right, the space on the outside and to maximize the amount of IMFs that can happen between water molecules, right? So surface tension, and if we think back to that penny lab, right, the way that it bubbles over the surface, right, that is the exhibition of surface tension, okay? We also talked about capillary action, right, where pretty much all of these are a measure of adhesion versus cohesion, right? Both have to happen. Other liquid properties also include, what was I going to say? I don't know, I forgot. Actually, you know what? We're just going to roll these in here as like a separate section, right? We have boiling point and we have melting point, right? Or we could call this the freezing point. That's fine too, right? So melting point and boiling point are also properties of, we could say, liquids or solids or both, right? And we also have our delta H of vaporization, and we also have our delta H of fusion, okay? Now, all of these are actually based on dun dun IMFs, right? In that higher IMFs, higher viscosity, higher IMFs, higher surface tension, higher IMFs, capillary action varies, right? Depends on what it's working through, but capillary action also a liquid property. Boiling point and melting point. Boiling point and melting point are higher if, right, if there are stronger IMFs. Vapor pressure, that was the other one. Right? And that is strictly a liquid property, right? Again, if we have a liquid, right, some of it is constantly vaporizing, right? And the amount of pressure, which means the number of molecules that basically turn into vapor, right, is dependent on the strength of an IMF, right? So anyway, and then likewise, these, right, are going to be greater if we have stronger IMFs. Yes, does that make sense? Okay. Solid types. So we have all of our different types of solids that your book goes over, right? We have our molecular solids, we have our ionic solids, and we have our atomic solids, right? Where molecular compounds, right, are going to be held together by IMFs, right? Which I think makes sense, right? And examples of these would be like what? Right. Sugar, or water, or I don't know, lots of things. We've drawn lots of them and talked about lots of them. Ionic compounds are clearly ionic, right? I don't know how else to say that. And they are held together by, we would say, electrostatic attractions, right? Where we have positive ions attracted to negative ions, right? And here, right, the concept of IMFs, so technically IMFs apply to molecular compounds, and that's what holds one molecule to its neighbor, right? So going back to water again, right? So what holds one water molecule to its neighboring water molecule is called an IMF, right? Whereas this is a covalent bond. That's not an IMF, right? This is what holds, these covalent bonds hold my water molecule together. IMFs hold one water molecule to its neighboring water molecule, right? Ionic compounds are a little bit different, right? Wherein if we have our Na and my Cl, right, it's harder to distinguish what holds one, because there is no concept of a single NaCl, right? So it's a whole network of electrostatic attractions, right? which is why, right, ionic compounds tend to have really high melting points and boiling points, right? Because that attraction is really, really strong because it's a network, right, of attractions. But IMF would not be the right word for that, okay? We have our atomic solids, which can be classified into three different types, right? We have our covalent ones, which let's call these covalent network compounds, right? Wherein we have kind of like these are a network of electrostatic attractions. Covalent network compounds are a network of covalent bonds, right? And this is generally going to be like our diamond and our silicone compounds, right? Where like in a diamond, right, every carbon is bonded to other carbons, which are then bonded to other carbons, right? And they are all held together by covalent bonds, right? Where covalent bonds are stronger than intermolecular forces, right? Which is why when we melt water, for example, we don't break this OH bond, we just separate one water molecule from its neighbor, right? Here, if my entire compound is held together by covalent bonds, right, it's going to be a much stronger force of attraction, which means that things like diamond, right, being the classic thing to think about, right? Diamonds have really high melting points. They are very strong, right? Diamonds are used in all sorts of drill applications, right? Because they are so strong and their melting points are so high, right? So we have our covalent network compounds, right? We also have our nonpolar compounds, which really these are just mostly going to be our noble gases, right? In terms of atomic things, right? Because atoms have to be our smallest particle, right? Molecular compounds are made up of molecules, right? Atomic compounds are made up of atoms. So these are really just our noble gases, right? And then finally we have our metallic compounds, not compounds, that's the wrong word. Our metallic elements, right? Which are clearly metals, right? Which are held together by metallic bonds, which your book describes as, right, a sea of electrons, better stated as a delocalized electrons. Delocalized electrons, right? So D meaning not localized, meaning not local, right? Meaning spread throughout the sample, right? So that means when I have a sample of copper, right, which is made up of copper atoms, right, the valence electrons of this will move here or here, right? And these valence electrons can move here and here. And so all the valence electrons are sort of shared between all the neighbors, which means that one atom can move relative to its neighbor. So this one could move up here without necessarily breaking any bonds, right? And if we're not breaking any bonds because, right, there are electrons everywhere, then we get properties like malleability and ductility, right, which make metals really useful for all the applications that we use them for, right? So anyway, so those are our different types of solids and a summary of our liquid properties. Let's go ahead and apply some of this to, heating curves. So if we take a look down here, what do we notice? Right, this is a cooling curve, right? Same exact idea, just going backwards, right? And then you might say, oh, well, that's confusing. Well, no, it's not, because we already know how to read and interpret one of these, right? So down here we have, well, up here we have temperature, right? So this is decreasing temperature now, right? And here we have time, which can also be heat added, right? And either way, it's the same thing, right? Because like I said, when we talk about heat added, we are talking about a constant addition of heat per time, right? Which means time would also be an okay x-axis label, right? Because it's like putting it on a hot plate and leaving it on a setting of 3, right? Where the amount of heat added doesn't change over time, okay? So anyway, let's label all our places, right? So let's say, ooh, we're so confused. It's cooling now. I don't know. How could we start? Right, let's label our plateaus, right? We understand that. What happens at a plateau? Right, phase change happens at a plateau, right? So here we have one phase change, here we have another phase change. One must be melting, one must be boiling. How do we know the difference? Right, this is higher temperature. At a higher temperature, we're going to have, right, that's going to be boiling or freezing. So we could label this as boiling or freezing. Nope, not freezing. Condensing. Right? Which means that this must be, right, this must be freezing or melting depending on which direction we're reading the curve. Yes? We're here, what do we have? right? Here we have gas heating or cooling. Here we have, right, that means this must be our liquid, and this must be our solid, right? So let's pretend that this is water. What other labels could we add? Right, this would be 100 degrees Celsius. This would be 0 degrees Celsius, right? And we know that this is going to be governed by the term, well, this is going to be governed by the term 4.184 joules per grams times degrees Celsius, right? This is going to be determined by my delta H vaporization. This is going to be determined by my delta H fusion, right? And then obviously we're going to have a C for my gas, which again you don't have to have memorized, but just to sort of finish out my curve, this happens to be 2.1 joules per grams times degrees Celsius, and this is, oh, no, this is 2.1 actually, and this one is 1.99, basically 2. Okay, yes. And so if we're going to think about any type of math, right, about heating, cooling, or phase changes, right, really all we're doing is we're envisioning a heating curve and thinking about where are we going and where are we starting. So let's say we're going to solve a problem here, right? So let's say this problem says we have an ice cube tray. It holds a total of 2 cups of liquid. How much heat must be removed to make ice cubes? So I want to make ice cubes from water that started at room temperature. So let's think about what all needs to happen. I have water at room temperature, which means it's starting at 25 degrees Celsius, right? And I want to make ice cubes. What has to happen to that water? Right, it has to get to 0 degrees Celsius, and then we have to freeze the water, yes? So we have 2 different and distinct steps that need to happen. So for this, that one's pretty simple, right? What are we going to use? Right, we're going to use Q equals MC delta T. And if we think about this curve, what that means is, right, we're starting somewhere around here. Let's get a different color. Starting somewhere around here, we need to cool it, and then we need to freeze it, and we're saying that we're going to stop here, right? Okay, so we're going to say Q is equal to the mass, which is 2 cups. And I did say you could Google cups to mils, right? Cups to mils happens to be 1 cup is about 237 mils, which means we have about 473 grams of water. And since it's liquid water, it's 4.184 joules per grams times degrees Celsius times 25 degrees Celsius, which means that the amount of heat associated with this is going to be 49494. And this should be a negative. This would be a negative, right? Because this is the amount of heat that has to come out of my water, right? Freezing. How do I figure that out? Going back over here, right? Freezing does not exhibit a temperature change because, right, no phase change is never a temperature change, because if we're boiling, all heat is going into breaking IMFs, right? If we're melting, all heat is going into weakening our IMFs, right? And if we think about in the other direction, so for example here, if I'm condensing, heat is being released, right, as IMFs are reestablished, right? Here, more heat is being released as the IMFs are more established, I guess. Yeah? Okay, so going back to our freezing, like it says here, we're going to use our heat of fusion, right, which for water happens to be 6 kilojoules per mole. So we're going to start with our 2 cups of liquid, which is 473 grams-ish of water. And then we know that for every 18.02 grams of water, we have 1 mole of water. And then we know that for every 1 mole of water, there's a heat of 6 kilojoules involved, right? Specifically, 6 kilojoules out. And this is going to give us 207 kilojoules. Now what? Right. We're going to take these, we're going to add them together, we're going to turn this into kilojoules, and then we'll take these, and my total heat is going to be, oh, no, never mind. This is actually 158. And then the total is this much heat must be removed to make my ice cubes from water that started at room temperature. If we look, there isn't actually a follow-up question. It says, what could you do to make the water freeze as quickly as possible? So sometimes our natural instinct is, oh, well, remove more heat, right? Which is not a thing, right? This amount is associated with this amount of heat removal, right? There's no way we can change the amount of heat to get removed, right? But what could we do? Right. We could make the ice cubes as small as possible, right? This is going back to that whole, like in your book, it talks about the rate of evaporation is governed by surface area, right? Likewise here, if we increase the surface area of my water, right, we can remove the energy more efficiently, right? So if we were to make tiny, tiny ice cubes like they have at the school cafeteria, right, my ice cubes will freeze faster. We're still removing this much heat, right, but my ice cubes will freeze faster, as in this much heat can be removed more quickly if we have smaller ice cubes, right? Ginormous ice cubes would require more time to get all that heat out, right, because we have to get all the way to the center of that ice cube. All right. Thank you for listening. Be good. Study, 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 and I'll see you soon. Bye.